everyone. You're watching the second part of the 21st lecture in the series Mathematical Methods for Economics. In the first part of the session, we talked about continuity. I gave you an intuitive sense of what continuity is all about, continuity of a function. We brought in the definition of continuity at a point. We talked about the various kinds of discontinuities, in particular removable and irremovable discontinuities, and we also talked about one-sided continuity. So moving on from there, what we'll talk about now is continuity on an interval. Because we have so far talked about continuity at a point, but in general you would want to investigate the continuity of a function over an interval. So let's examine how that is going to be done. Now the interval as such could be an open interval, or it could be a compact, a closed bounded interval. So let's see how the checking will differ in the two cases. And look at the slide here. So a function f is continuous on an open interval I if and only if it is continuous at each point in that open interval I. Okay, and on the other hand, if you're talking of a compact interval, a function f is continuous on a compact interval a comma b. It is closed and bounded. That is to say, it includes its end points. So a function is continuous on a compact interval if and only if it is continuous at each point in the open interval. So the first part of the definition that you have here in this slide also comes in. And at the same time, the function also has to be continuous on the right at a, because you also have to have endpoint continuity. But because you're not going to be moving to the left of a, so the function has to be continuous on the right at a and on the left at b. Okay, so if we are checking for continuity on a compact interval, we'll also have to check for the endpoints. So let's look at an example to see how we go about doing this. And here we have a function which is given by square root of 9 minus x squared. So actually, if you just visualize this or just draw it, it's nothing but a semicircle. And you can see here that the domain of the function is going to be this compact interval minus 3 comma 3. Right, because 9 minus x squared has to be greater than or equal to 0, which is to say that x will lie between minus 3 and 3. To check for continuity of this function, we'll divide our exercise into two parts. First, we'll check for continuity on the open interval, minus 3 to 3. How will we do that? Let's just take a random point A in the open interval minus 3 to 3. Okay. Now, what is the criterion for testing for continuity at a point? Simply that the limit of the function as x tends to a has to be equal to the value of the function f of a. And you can see here that the limit of the function as x tends to a is nothing but the limit of square root of 9 minus x squared as x tends to a. That is 9 minus a squared, which you can see here is the value of the function itself at x equal to a. So this establishes continuity on the open interval. Now, how about continuity at the end points? So we have to now check for continuity at minus 3, where we're going to check for right-sided continuity, and we'll check for continuity at 3. So I've done the 3 part first. So to check for continuity at the end points, let's say 3, here you're going to look for left-sided continuity. So the limit of the function by definition as x approaches 3 from the left, that has to equal f of 3. Right? Now, what is f of 3? F of 3 is nothing but 0. So let's see what the limit of the function is as x tends to 3 from the left. That's nothing but the limit of square root of 9 minus x squared as x tends to 3 from the left, which is actually 0. Similarly, the limit of the function x tends to minus 3 from the right, that also has to be equal to 0, because that's the value of the function at x equal to minus 3, and that actually is the case. So here we have that the function is continuous. The conclusion is that the function square root of 9 minus x squared is continuous in the compact interval minus 3 comma 3. So here you have to do the checking for the open interval as well as the endpoints, and if you have continuity for both situations, then you can conclude that the function is continuous over the entire compact interval. Okay, the next thing we're going to do is we're going to discuss some properties of continuous functions. These are really, they really come in handy. And what we'll do is we'll start with the continuity properties of, we'll just take up some simple functions. And then we'll go on to show that algebraic manipulations of continuous functions are also continuous as long as a function is defined. For the relevant portions for which we're checking continuity. Okay, so the condition that we're going to use throughout to check for continuity for the simple functions is just simply the third condition, because as I said, that's already taking into account the first two conditions of our definition. So we'll just check for the limit of the function as x tends to a, is that equal to f of a. Our first function here is f of x is a constant, and we are claiming here that it is going to be continuous everywhere. Similarly, the function f of x equal to x, that is also going to be continuous everywhere. Now, before we do the math, just think, always try to think of things visually. What will happen here? If you draw either one of these two functions, f of x equal to c or f of x equal to x, these are nothing but straight line graphs, right? F of x equal to c is just this flat line, right, at the height c, and f of x equal to x is going to be the 45-degree line passing through the origin. So these are straight line graphs, and visually you can straight away see that these are going to be continuous everywhere. Now, can we prove that using the definition? Yes, of course, because limit of the function, let's take the function f of x equal to c, that limit, because the function is a constant everywhere, that is simply going to be c, and this is again the value of the function at x equal to a. Similarly, if we take the function f of x equal to x and check for continuity at the point x equal to a, then the limit of the function as x tends to a is nothing but a itself, right? And that is again equal to the value of the function at a. So these two functions are continuous everywhere. We can then extend this discussion to a polynomial p of x given by cn x to the power n plus cn minus 1 x to the n minus 1 and so on till c1 x plus c naught. So this polynomial will also be continuous everywhere, because you can clearly check that the limit of p of x as x tends to a is going to be p of a. And what we're now going to do is we are going to come up with these results on continuous functions. So we'll do some algebraic manipulations of continuous functions, and we'll show that these algebraic manipulations are also going to be continuous for the points where these functions are defined. And here what I'll do is, so let's go over these results first. We have here that if the functions f and g individually, if they are continuous at x equal to a, at the point x equal to a, then the sum and difference of these functions, so f plus g and f minus g, are also continuous at a. F times g is continuous at a. F divided by g is continuous at a, as long as, remember, that the denominator is not 0. Okay, so f by g is continuous at a as long as the denominator is not 0. And finally, f of x to the power p by q is going to be continuous at a, at the point x equal to a, if f of a to the power p by q is defined. Now, what I'll do is I'll walk you through one of the proofs. Let's do the first one. And the remaining proofs you can just work out on your own in the same way that I'll show you this proof, just by using the definition of continuity and the theorems on limits that we have done in the earlier classes, in the earlier lectures. So let's look at this first result. We are saying that if f and g are individually continuous at x equal to a, then the sum or difference, so f plus minus g, I'm just writing them together so that we can go faster with the result. So f plus minus g will also be continuous at a. Now, what does it mean for f plus minus g to be continuous at a? I simply have to prove that the limit of f plus minus g as x tends to a is a value of this function at x equal to a. So that's f of a plus minus g of a. Okay, so let's look at the proof here. Now, because the functions are individually continuous at x equal to a, so we have that the limit f of x as x tends to a is f of a, and the limit of g of x as x tends to a is equal to g of a. So let's see what happens when we calculate the limit of f of x. And remember that both these, because both of these functions are individually continuous, and both of the limits are equaling finite values. So the limit of f of x plus minus g of x as x tends to a, that's the limit of a sum, right? That is going to be, if you remember the properties that we did under the limit section, the limit of the sum is a sum of the limits, and because you're dealing with finite values, that rule is going to come into play. The limit of the sum or the limit of the difference is a sum of the limits or the difference of the limits. So that's going to be equal to limit of f of x plus minus limit of g of x. And because limit of f of x is equal to f of a as x tends to a, and the limit of g of x as x tends to a is g of a, so there you are, your result is right in front of you. Okay, and in the same way, these are very simple proofs, so I have left the rest of the results, the rest of the three results to be proven by you yourself. So let's move on and let's talk of the other results. So this is related to the third point that we made, that if you have a rational function r of x equal to the polynomial p of x divided by the polynomial q of x, that is going to be continuous for all values of x as long as the denominator is not equal to 0. Right? So this is a very important point which we'll take into account in one of our problems that we just do. Now this result here, the last result on this slide, this says that if you have a function g, this is a result of composite functions actually. So if you have a function g which is continuous at x equal to a, and f which is continuous at g of a, then the composite function f of g of x is also going to be continuous at x equal to a. I'm not going to be doing this proof with you, but keep this result with you if it needs to be used. Right, so let's work on this problem, and this actually is an interesting problem because it brings in our properties and it also helps you work through your concepts of removable versus irremovable discontinuities. So here you have, the question is, let's look at the function first. So here you have this function f of x equal to x squared minus 1 divided by x squared plus x minus 2, and clearly you can see this is a rational function. You have a polynomial divided by a polynomial. So the question asks you for what value or values of x is this function discontinuous. Okay, and determine whether the discontinuity that you have, that you discover, are those discontinuities, or is that discontinuity a removable discontinuity or an irremovable discontinuity. Now, first of all, note that the rational function is continuous everywhere except where the denominator is 0. Now, what is the denominator? X squared plus x minus 2. And actually, you can factorize this to see that this function can be written as x squared minus 1 divided by x minus 1 times x plus 2. So this function, you can see, is a rational function, and let's invoke the property of rational functions, that is going to be continuous everywhere except where the denominator is 0. So where is the denominator 0? Where either x minus 1 is equal to 0 or x plus 2 is equal to 0 or both. So the function will be continuous everywhere except where x is equal to 1 and where x is equal to minus 2. Okay, so these are the points of discontinuity. The question now asks you, identify whether these discontinuities are going to be removable or irremovable discontinuities. Now for that, first of all, note that you have a common factor in this function. You can write this function in the numerator, you can write x squared minus 1 as x minus 1 times x plus 1, and you can see that the x minus 1 terms will get cancelled, so that you can write this function as x plus 1 divided by x plus 2. What is happening here? See, if x is equal to 1, because you have a common factor here, you can see here that your function is collapsing to 0 by 0 form, right? If I put x equal to 1 in the numerator and x equal to 1 in the denominator, I get a 0 by 0 form. F of x just collapses to 0 by 0, which is not defined. Okay, so here I have a situation where x equal to 1, for x equal to 1, the function is not defined. But yes, the limit still is. So if you notice here, I can still calculate the limit of the function as x approaches 1, because I have, after removing the common factor, the function can be written as x plus 1 divided by x plus 2. So if I take the limit of this function as x tends to 1, I'm going to get 2 by 3. Right? So this is a classic case of a situation where you have a removable discontinuity. See, the function is not defined at x equal to 1, but all I have to do is just redefine the function. So let's say, let's redefine the function to say that if x is equal to 1, then the value of the function is 2 by 3, which is nothing but the limit. And that will take care of the continuity, the discontinuity, and you can remove the discontinuity. I hope that's clear. And look at this other point where we had a discontinuity, which is x equal to minus 2. Now here, this discontinuity is going to be irremovable, because if you notice here, the problem here in this case is not the first condition not being fulfilled, it's the second condition. The limit of this function, so if I still look at this function as, let's say, x plus 1 divided by x plus 2, the limit of the function as x approaches minus 2 is either going to be infinity or minus infinity, depending on whether x approaches minus 2 from the left or from the right. And this discontinuity is the more serious one, and it is an irremovable discontinuity. So I hope you've understood the criteria that are to be used to figure out whether the discontinuity is removable or it is irremovable. Okay, now I have this example, which is a classic one from the book R.G.D. Allen, and it's also appeared in one of the Delhi University exams. So here you have a function which is given by the limit of the expression 1 by 1 plus x to the power n as n approaches infinity. And here x takes on all positive values, so x is strictly greater than 0. The question asks you to sketch the graph of this function and locate its discontinuities. Now, a useful strategy to follow when you have questions of this type, where you have x positive, is to actually break up your x into different parts. So, because when when you have x to the power n and n is approaching infinity, the expression is going to behave differently when x is between 0 and 1 or when it is greater than 1. Right? Because if you have something between 0 and 1, then that if you take the powers as n approaches infinity, that's just going to tend to 0. So let's take a look at these cases that we've built up. So I have this first case where x lies between 0 and 1. Now if that is the case, then clearly x to the power n will tend to 0 as n approaches infinity, right? Take any small value of x which is between 0 and 1 and keep multiplying it with itself, and that will just become a smaller and smaller value. So x to the n tends to 0 as n tends to infinity, which is to say that the function is going to take on the value 1, because the limit of 1 upon 1 plus x to the power n is simply going to be 1, because x to the power n tends to 0. On the other hand, if x is strictly greater than 1, in that case, x to the power n will tend to infinity as n tends to infinity. So if that is the case, then the denominator here, if this expression goes off to infinity as n tends to infinity, your function is going to take on the value 0, because the limiting value of this expression is going to be 0. And the third case is 1, because we also have to take into account what happens when x is equal to 1. Now note here that when x is equal to 1, this expression 1 divided by 1 plus x to the power n is nothing but 1 divided by 1 plus 1 to the power n, right? And that is nothing but 1 by 2, because any so you have a constant here as a base, which is 1, and the constant 1 raised to the power n, which can be any number, that is itself going to be 1. So that's going to give you a 1 by 2. And when I take the limit of 1 by 1 plus x to the power n as n tends to infinity, that's going to be nothing but 1 by 2. So when x is equal to 1, the function has a value 1 by 2. Okay, so we are now all set to graph this function, to draw the graph of this function. So you can see here we have three parts in the function. If x lies between 0 and 1, the value of the function is 1, and that is exactly what you have here. The height till 1 is 1. At x equal to 1, the function value is half, which is given here as 0.5. And for x strictly greater than 1, the function becomes 0. So here I have this, it's a step function. With this at x equal to 1, you have a point here in the middle as well. But I don't know if it's visible, but there's a blue line here on the x-axis, which is to the right of 1. And because these endpoints are not included, I have these open circles here. So I hope the graph is clear, and it's clearly a discontinuous function. So this is a nice example to get your understanding right when you're, when you have to, because these are kinds of situations which also come up in other areas in economics. So this is a good strategy where you break up the analysis into these three parts. Okay, so what I'm going to do is we'll do one last example in the time we have left, and this is basically again going back to a basic intuitive understanding, but I thought it's an interesting thing to talk about. So here the situation is that you have an aeroplane which is flying over a bridge, right? And the bridge is built on a road. So the question asks you, is the height of an aeroplane above the point on the bridge or the ground vertically below, is that going to be a continuous function, right? So if it's like it's an aeroplane flying over a bridge, and the bridge is built on a road. So the height, the vertical height of the aeroplane from the bridge or the road, whichever is closer, that is what the height function is capturing. So what we're asking is h a continuous function of x as we proceed horizontally? Okay, so here the answer is going to be, again, not necessarily, because you may have a situation like this. So I have this picture here where actually the bridge is broken. So the aeroplane is flying over the bridge, right? But do you see that when it's going to reach this point, so far the vertical height is it's a constant because the bridge is of the same height here. But the moment the aeroplane reaches this point where the bridge is broken, the height is suddenly going to jump. It's going to jump to this entire vertical area, and let's assume the road is here at the bottom of this picture. So you can see that there is a jump in the graph. So the height of the aeroplane, where we are talking of the vertical height from the bridge or the ground below, is that's not going to be, in this case, it's not going to be a continuous function. But then we can actually just tweak things a little bit, and let's suppose we are talking not of the vertical distance, but the nearest distance of the aeroplane, the distance of the aeroplane from the nearest point on the bridge here. Then if you just visualize that actually is going to be a continuous function. So if you just take the nearest point to the bridge here, and that will then give you a continuous function. So that's all we have time for today. Time to close the discussion now. Okay, bye-bye.